Hey guys, this is part 2 of how to do science. Please watch the other video first and then come back to this. In this video, we are going to finish up the last 2 bullet points, learn how to analyze our results and how to communicate them to others. So I want to preface this video. This stuff is tough. These are going to be your faces. At first, you're going to be like, what the heck are you talking about? Then you're probably going to start crying a little bit and be like, why did I take AP Bio? And then you might be like, I'm not even going to finish watching this because I'm just never going to understand that. But you're not supposed to by the end of this video. This is an intro. It's going to give you the big ideas of what this stuff means. And then we're going to be using it all year over and over again. And by the end of the year, this is going to be you. One thing, some advice I want to give you, we are going to do these things on every lab we ever do. So every time you see it, try to get a little bit better at it. And over time, it will become easy. In the last video, we left off at how do we collect data, and I told you need to organize your information while you're conducting the experiment into a data table. And so the experiment that we're going to focus on for this part is this experiment, and our scientific question, remember, was, let me write it for you. So remember, I'm not going to write the whole thing, the difference between plants in sun and shade. And not just the difference in plants, but the difference in leaf size. And so let me give you this experiment. There is a student and she lives in this area and she notices that there is a certain plant that grows where she's at, and on one side of the house that never gets shade, there's this plant, and on the other side of the house, there is this plant that always gets shade. And she kind of noticed that there might be a difference in the sizes of the leaves. And she was like, is there a difference when they're growing in different amounts of sun? And so she took a sample size. She took a sample from the shady leaves and she took a sample from the sunny leaves. And remember, she's not measuring every single leaf there is. She just picked a random sample and measured them in centimeters. And so that's going to take us to our next slide. We talked about how important sample size is. And the purpose of that is because when you are sampling something that is part of a bigger population, you want to make sure that your sample is representing the entire population, so that if you are going to come to a conclusion, you can make that conclusion based on the whole population and not just the little group that you chose. And so your sample size, your sample, after you so here she took her data table and she graphed it into this bar graph. So here we see, and what she did is she put them in order. So all of the plants that were about 4 to 5 inches, 5 to 6 inches, 6 to 7 inches, and how many of those leaves that were that size, she graphed it from the 2 different populations. And she got this curve. And this is called normal distribution. This is what you want. And this is what tells you that your sample size is most likely representing the population. Because what it's saying is that around here, most of the plants are around this size. She has a lot of plants this size, and then it tapers off on the edges. And that's good, because think about it in a different way. Let's think about height. If we're looking at the height of humans, we know that this would be around, for males, let's say 5'9". We know that average size males are most likely around 5'9", but then you also have very, very tall males. So my husband is 6'7", so he would be an outlier. And you also have very, very short males, like the guy that's on 30 Day Fiance, that's like 4 foot or whatever. But the average, it should be, most of the population should be clumped up around the average, the middle. So again, the purpose of this step is just to make sure that you got an even spread. That's it. It's not giving us any answers. If we're asking about does the sun have to do with shady versus sunny leaves? We can't really tell. We have this big one here of sunny leaves that are bigger, but that's not really representative of the whole population because there's lots of other things going on there. So the next thing that we're going to have to do is we're going to have to do some other descriptive statistics to help us answer our question. Once you know that your sample size is a normal distribution, then you can apply statistics to it. And the first thing that you're going to want to find is the mean or average. The mean is a calculation to tell us on average how did where are most of the individuals at. How do you find an average? You add up all of the individuals and divide it by how many are in that population. So you would add up all these numbers and then you would divide it by how many there are. And I didn't count to see how many that is, but I think you guys know how to do average at this point. And all that's telling us is an estimate of the population's mean, but is an average enough to answer our question? Remember, our question is, does leaf size differ in sun versus shade? So most likely, I mean, there's a lot of numbers here, so it's kind of tough, but most likely, I don't know. If you're just eyeballing and you have like 8s here, you have some 8s there, you have 10s. It kind of looks like they're different. So this one will definitely have a higher mean than this one. Let's just say it does. But just because there's a difference in the mean, that is not enough information. Think about this. If you had a population and let's say you calculated the leaf sizes are 10 centimeters and then you have 20 centimeters and then you have 2, 2, 2, 2. Okay, if you calculate it and you add up all of them, divide by the total. So there's 1, 2, 3, 4, 5, 6 individuals, and you get 6.3 centimeters is the average. Okay, but let's say there's another population. Let's say you measured and there was 6, 7, 5, 6, 6, 8 centimeters of these leaves, and you find the mean. The mean that you get for this population is also 6.3 centimeters. It's the same mean, but look at the population. This population looks a lot different than this population. Like mostly these are like very small. There's just a couple outliers, but here they're all kind of around the same point. So mean is not enough by itself because it does not represent what the population looks like. So just by comparing the mean of the shady leaves versus the sunny leaves, it might not give you enough information. So after you find the mean, you're going to want to find the standard deviation of the mean. And what the standard deviation is a measure of, it is a measure of, I'm sorry, I'm changing my pen, the spread in the sample population. So it can tell you the variation of the entire sample set from the mean. So for example, let's look at this figure. This point right here, because remember we did our normal distribution, that's the mean, the top of the bell curve. And standard deviation is going to measure how far away the spread is from that middle point. So let's look at this picture down here. In this English class, the standard deviation is 7.5. The mean right there is 100. And you can kind of see that most people kind of scored very close to 100 because the curve, the standard deviation curve, is very close together. It's not very spread out. Here, the standard deviation is a little bigger. In math, the average is still 100, but you can see that more people kind of did like really good and not so good. As opposed to physics, yikes, even with the average still kind of seeing that bell curve at 100, there's a lot of people away from that score. That is what standard deviation is telling us. So The less variance and close to the mean, the smaller the deviation. So like this example here, see how it's smaller deviation, it's those sample individuals are closer, they're bunched more up around the mean. If the standard deviation is high, then you're going to get something like this, where from the mean, there's going to be a lot more individuals kind of spread out from that. So it gives us an idea of what our sample set kind of looks like. And so just to get into some of the numbers here, in the yellow, right here, this is most numbers. This is C of the 1 right there. So 1 standard deviation below the mean and 1 standard deviation above the mean, about 68% of your population if your sample size is going to be in there. And then 2 standard deviations, so that's this, all of that. So if you go to the mean, you subtract 2 standard deviations and you add 2 standard deviations, that's going to be about 95% of your sample population is going to fall within that range. And then 3 standard deviation is going to be 99%. You shouldn't have any, like, very little outliers past that point. So if we're talking about 1 standard deviation, we're talking about most of your we're talking about 68% of your population. If we're talking about 2 standard deviations, we're talking about 95% of your population. And so that is just ways to talk about the data that you collected. Now, this is the calculation for standard deviation, and we're not going to do it right now, but this is what it looks like. And just so you know, this right here is the mean. So you're going to plug that in. This is the value of the data set. This is the sample size. And this guy right here means summation of. That means add it up. So I'm not going to go through a calculation here. I just want you to focus on what it means, but you will see this coming up. So when you graph standard deviation, if you ever need to, what it's going to kind of look like is you'll have your graph, and you still you would graph the individual numbers here. So like, I'm not going to make this pretty. That would be 10, 20 is going to be double that, and then you have 2, 2, 2, to get these. And we know our mean is 6.3. We would use that, and we would calculate our standard deviation. And how you would draw your standard deviation is you make it into a bar. So let's say this was our 10. Let's say, for example, our standard deviation was 1. From the next stat that you want to find is standard error of the mean. The standard error of the sample mean is an estimate of how far the sample mean is likely to be from the population mean. So we are going to figure out what this means. We know that when we are doing an experiment, we take a sample size. And when we are coming to a conclusion about our experiment, we are basically saying that our sample size that we took is a representation of the whole population. So if we studied every single one of these leaves, we would get basically the same answers, what we are saying. So standard error of the mean is a statistic to help us figure out how close our sample mean is from the actual population mean. It's a way to describe it. So if you look at this graph, we have 2 populations here, the woodruff and the popka, and then we have our males and our females in each one. And I don't know what this experiment is, but we're just going to learn how to use standard error of the mean with this. And the standard error of the mean is represented in these bars. And it is drawn away from this. This bar is the mean. So this number right here, a little bit over 180, is the mean of the males in this population. This number right here, 280 is the mean of the females in this population. And these bars are representing the standard error, and it represents how close this mean is to representing the whole population of males in Woodruff. So you're going to see it, and you're going to see this plus or minus 1 SE, or it could ask for plus or minus 2 SE. In AP Bio, you may have to calculate this, and I did not put the calculation up here because I don't want to freak you out. But I'm going to give it to you on this, and we'll talk about how to figure it out later. So what you need is you need your mean. You would have to find your standard deviation to calculate it, but you don't really need it for anywhere else, so I'm not going to include it. So let's say it's 6 again. And let's say we calculated our standard error, and our standard error was 2. So this plus or minus 1 SE is from the mean. I don't think my pen works anymore, guys. Plus or minus 1, and in this case our SE is 2 from the mean. Our mean is 6. So that would mean we would get 6 plus 1 times 2 would be 8. And we would get 6 minus 1 times 2, which equals, we would get 4. And so if I was going to graph this like the one above, you graph the mean. So let's say it's 6. There's the mean. Oh, I don't want to do that. So from the mean 6, you go up 2. And that number right there is the 8. So these numbers are giving you where to plot. And from the mean, you go down 2. And that would be 4. So again, these numbers that you're finding here are what you're going to graph. So if it was plus or minus 2 SE, so now you have 6 is the mean, plus or minus 2 SE. Our SE is 2. So if I was going to graph that, so right now this is 1 SE, so I'm going to draw a new graph. If you're graphing 2 SE, there's our 6. There's our mean. From the mean, which is 6, you're going up 2 SE, which the first one would be 2 times 2 is 4. So 6 plus 4 is 10, so this number right here would be 10. And then minus 4, so it would go down to, that number would be 2. And this is plus or minus 2 SE, and that's showing us how close this mean of our population is to the actual population mean, our sample mean. This is our sample mean to the actual population mean. And the number doesn't mean anything totally, it's more of a representation, because I'm going to show you on the next slide how we use it. So now let's kind of do a little review, and what is the difference between standard deviation and standard error. So again, standard error of the sample mean is an estimate of how far the sample mean is likely to be from the population mean, whereas standard deviation is the degree to which individuals within the sample are different from the sample mean. So let's look at these graphs down here. So notice this one here, this graph is talking about standard deviation. That's what these bars are. So this says 8 boys, that's the population. And then you have this little tiny bar here that's kind of, you can see it drawn, it's very small. And so it's showing you, since we're talking about standard deviation, that I can't read this one, so we're going to make something up, but whatever this is talking about, the boys are not very spread out. There's a very small standard deviation here. So most of those boys are around that area, that mean. As opposed to the girls, they have a larger standard deviation, meaning that the data from that sample size of the girls, there's a lot of variation from the mean to the like individuals in that population, that standard deviation. Over here, we're looking at standard error. And it's different. It's telling us something different. We have a population here, sunny and shady. The standard error now is telling us that this is kind of how close the sample mean is to if we were going to apply this to a real life whole population, which here maybe we only calculated 30 in our sample size and the whole population is actually 1,000. This one means like pretty close. Same thing here. This is the mean population of the leaf size in the sunny, and this is the standard error, meaning that it's pretty close to the population. How do we use these bars though? Because it's not giving us a number to use. It's not saying like it's 2 away from the population size. These bars are just a way to study the graphs. So let's look at this. This is really important right here. Overlapping error bars. When the values of error bars overlap on a graph, it means that there is not, this needs emphasis, there is not a significant difference in average of those data sets. So here, do you see how the bars are overlapping? I'm going to delete this. Circles I drew. Oh no. Okay, close enough. If I drew a line from the top of this standard deviation bar straight across, see how it overlaps with the girls? That means that this mean is not significantly different from this mean. So we would not be able to say that the boy population is different from the girl population because they're overlapping. Even though we have a difference in our means and our averages, it's not different enough to say that there is a difference between the two. Let's think about this statistically. If I flipped a coin 100 times, the probability would be that it would be 50-50 heads and tails. Now we know that if I actually flipped a coin 100 times, it would not land 50-50 perfectly. It would be like 48-52. You would have a different mean. But the question is that difference enough of a difference to say that those two populations or those two groups are actually different from each other, or is that by chance? Since this is overlapping, it means that the difference between the girls and the boys in this situation is not statistically significant. Those differences are due by chance alone. Now let's look over here when we're talking about these two populations. Again, if I drew my line straight across, it's not overlapping. There is no overlapping. So we can say that this difference in these two populations is enough of a difference to say statistically there is something going on there. It does not prove your hypothesis, but it tells you that it is supported. If, for example, let's say the standard deviation for this one was actually like this, and when we draw our line across from the one error bar across, now it is overlapping. So if it was overlapping like this, then it would mean that these two are not significantly different from each other. That the differences in the means and the populations are actually due to random chance. So let's sum up what we have done so far. We went from collecting our data, our scary looking data table. We figured out what the average was of the two populations, but we realized that these numbers, we can't really rely on just the average. So we figured out the standard deviation to see the spread of our data. And then we figured out the standard error so that when we graphed it, we can see if it was a representation of the population mean, and we can compare them in a more accurate way, meaning that the differences in the means actually are significant.